Okay, so let's write down the conclusion of our discussion last week. So if f of x is continuous and absolutely integrable over the formula line, and if a of b, b of b, and p squared of b, p squared b of b are absolutely integrable on this semi-infinite interval. Of course, a and b, they are Fourier cosine transform and Fourier sine transform, respectively. Then this integral, okay, this comes to a function of s and t. Okay, so this is integral. Is a solution of the heat equation and satisfying the initial condition here. So that is the result we have. And so the next we would like to rewritten the integral expressions into a form directly expressed in terms of the initial temperature f of x here. Okay, so we want to do so. So now, so substituting. Right, so now we would like to substitute the expression to formulas for a of p and b of p into this integral. So we have okay, plus okay, e minus c squared p squared t dt. Okay. Just a direct substitution. And so, so now one part you can factor out the common constant. Okay. Right, and merge these two terms together. So we have cosine dv, cosine dx. Plus sine dv, sine dx. Okay. And dv here. Okay. Exponential minus c squared p squared t dp. So this integral, the inner integral is over v, and the outer integral over p. And so now you have, by using the product sum formula, this is equal to cosine p x minus v. Okay, so this is cosine p of x minus v here. All right. So we have 1 over pi. F of v cosine p x minus v and we can read exponential. Right. So we have that. Okay. And we can exchange the order of integration. Okay. As I mentioned by Buffin theorem, is that if this order, if we take the absolute value, okay, we take the absolute value, and we know that this is the most is 1, right? And this is the most 1. So this is less than or equal to the absolute value of f3, and we know f3 is f is absolutely integrable. So of course you can integrate everything there, and so that we can exchange the order of equation. So we have cosine p x minus v sorry, this is p, sorry, the dp and the dv. Okay, and this is the book by Buffini. Okay, so and recall the formula. Equal to square. Okay. So I just write down the identity. So this is special type of improper integral. Okay, e to the minus s square and cosine 2bs. Okay, these parameters and dx. So this integral actually is equal to this quantity. And well, okay, and so we can see that the inner integral. See here. So we have so basically the x is pretty much like p. Of course, you have to do some manipulation. So so by so let me see. By letting x equal to c squared tp. Remember, t is greater than or equal to 0, so it's cp. We have xt equal to f of v 1 over 2 c square root of pi t here. Okay, exponential minus x minus v 2c squared t square and the dv. Okay. Right. So we can see okay. Because that we let this one to be equal to x squared. Okay. So when we let this is equal to x squared, so we need to use this changeable variable. So x is equal to c times square root of t times p here. And we know this one should be equal to 2ps, right? 2ps. So this is equal to 2 times b, and s is equal to so s is equal to c square root of t and p. Okay? So 2 times b times c times square root of t times p equal to this one. So this is implies that implies x minus b equal to 2c square root of t and b. So this is implies that b is equal to 2c square root of t x minus b. Okay. All right. And so the integral is equal to this one. Okay. And so this move to here. And the square root pi, so we have square root pi here. Okay. And the dp, here dp, this is equal to 1 over c square root of t and ds. Okay, think of that. Okay. So dp is replaced by this quantity, so that's why we have c square root of 2. And 2 here and pi here. So together, we find a very simple and nice expression, like this one, by using this formula. There are quite a few ways to find the formula. Okay. One way is that, well, if we you can look at that. This is an even function, right? Even function. So you can extend the interval to infinity. And also, if the same, so from minus infinity to infinity, take a half. Now, the same exponential term times sine function, but the sine function is odd, so it's 0. So you add the term will be the same. Okay, and so it's just like a Fourier transform. All right. So let me give you an idea here. Actually, okay, so you add this term because sine is odd function. So odd function times even function becomes odd function, and when you do the integration, it's 0. Okay, so you have to. Okay, you have that. And actually, this is related to a Fourier transform. Okay, so you can check the Fourier transform table to find the results. Okay, so you can go back to check your Fourier transform table because well, so is the Fourier transform this one, and we know for Fourier transform it is actually 2 fx, right? So the f is minus 2b, so you can and 1/2. So you can evaluate that. And after we know how to do, because then you have a complex exponent, okay? So we can do the integration by the residual integral in complex analysis. That's very easy to evaluate. But right now, we still don't know how to do it, right? But actually, you can do. What now you can do is by checking the Fourier transform table. You can check that to find the result. But later on, after we introduce the residual integral, right? In complex analysis, then you will know how to evaluate this integral in several steps, okay, to find the result. So just to give you an idea, this is not a difficult part. This is actually an easy part to get the fact about that. But temporarily, you just accept that this is a fact, okay? And then so we get around with this integral like this one. Okay. So this is a good formula you can use. Okay. Also, by relating z equal to v minus x and 2c squared t. We have u xt equal to f x plus 2c z square root of t 1 over square root of pi e minus z square dz. Okay. All right. So this one, this formula is particularly useful. Why? Well, you see, u x0, okay, u x0, right, is equal to, so you have f of x here, because when z is 0, this is 0, and when t is 0, this is 0, okay. And 1 over square root of pi e minus z square dz. Okay. All right, and so this is independent of okay, and I will give you an idea by some by change of variable. Here z is equal to y divided by square root of 2. Okay? You have that. And this is the so-called the standard Gaussian probability density function. Okay, maybe it's too early for you to know about that if you don't know the. But if you remember, I suppose that you know what is the standard normal distribution in high school, right? I believe you still remember. This is the standard, okay? Gaussian distribution or standard normal distribution, because this is a random variable with this distribution has zero mean and the variance 1. Okay, and so this is just the total integration of the probability density function. So the integral is equal to 1. If you still remember something in high school, okay, because the density is bell-shaped. Remember that? So this is okay. So this is the probability density function. It's the so-called the standard normal distribution. And for a standard normal any probability distribution, the total integration is equal to 1 because the total probability is equal to 1. Right? So you have f of x. So we get the initial condition, right? Because this should be the fact, right? Because ux0 should be equal to f of x. So exactly we get that, right, from this expression. So we have two useful expressions here. One is this expression. The other is here. Okay. They are. Now, yes, please.
上面那个表达的那个根号还是在分子。
This one? Yeah, square root. You mean here? No, because here, because x dx is equal to c times square root t dp, right? So dp is equal to 1 over c square root t dx. Pi, okay, pi is here, but we have 1 over pi here, right? Yeah. Thank you for asking. So it's very hard because it's quite they are quite distant from each other. So that's why. Okay. So you have this and this one. Okay. And now you can verify the solution by this one or by this one. So actually you can do it by this expression to show that. So this one implies that if f of x is bounded, okay, for all x in R and integrable in every finite interval, then so let me see. I forgot our equation number. Is this 12.7.6? I suppose because I think we used up to 5, right? Yeah. 6, so this is 12.7.7. Okay, so then the function in 12.7.6 or 12.7.7, okay, satisfy 12.7.1 the heat equation and initial condition. Alright, so with this expression, we can enlarge our solutions to include the initial condition, which is bounded, just bounded, and integrable, alright, in every finite interval. Okay? For example, f is a constant, is result is 1. Okay, it's 1, then you still get the result because it is uniform. If you have a uniform temperature, right? Then you get the uniform temperature too. It's equal to 1 because if you have uniform temperature as initial condition, initial temperature, then you will stay there, right, forever. Because there is no heat flow. So the temperature will not change physically, you know, right? But if F is a constant, F is not integrable, right? Over the whole real line. So it cannot satisfy the condition here, right? Because the condition is more restrictive. Why? Because we use the separating variable method. Initially, we use the separating variable method to get to this point, right? By Fourier analysis. Okay, so we have we need a stronger condition for us to end up with this solution. Because there are a lot of steps, right, to follow. Okay, so, but once we find some solutions, it is possible to extend the solution to other initial conditions, right? So we have this form because this is satisfied for any F, satisfy this all the conditions here. So here so we can prove, okay, that we can prove that if F is bounded and is integrable in every finite interval, it's not required for FF to be absolutely integrable over the whole real line. Okay, so this is very practical, and I just demonstrate one situation like if f of x is constant, it's just a constant temperature. Okay, in this case, then this is constant, say 1. So you pick it out, and then the integral is equal to 1 because the integral is equal to the integral of the standard normal distribution. It's equal to 1. So that's fine. Okay? So this it's not hard. Okay? It's basically you can start with this definition of the function u, and you see that immediately you can verify the initial condition is satisfied. Okay? And then you can do the differentiation. I think you can adjust that. You can because I provide a theorem. Okay, here theorem 12.7.8, right? So you can do the differentiation under the integral sign. You can do that. And to reach your result. Okay, so any questions? So this is a very common technique that, because separating variable is a very simple method. So it will give you a very strong result solution with some strong conditions. And then you can weaken the required conditions to get more solutions for the same PDEs. Okay? In fact, we can use Fourier transform to solve the heat equation of a form extending to the whole real line. Right. So we can use Fourier transform to solve the equation of a bar extending to the whole real line. And if the bar extend only to the positive half axis, then Fourier cosine or sine transform can be used instead. Okay, so I will demonstrate how we can use Fourier transform or Fourier cosine or Fourier sine transform to solve partial differential equation. Okay. I will do it quick and let you to check all the necessary, all the required conditions to let it happen. Okay. So so consider the whole real line first. Okay. Okay, so now we will. Okay, so so now with t as a parameter, right? So we have Fourier transform. So I use the subscript to say that this Fourier transform is respect to the variable x. Okay. So now ut equal to c squared uxx. Okay. So I take the Fourier transform of both sides, all right? And now, because t is a parameter, so u is regarded as a function of x, okay, as a function of x. All right, and so for here, this is the second derivative, right, with respect to x. So by our differentiation theorem, this is equal to square u. Okay, and of course, to have the differentiation theorem, there are some conditions for u, right? And let it open for you because that you can check back to the differentiation theorems we discussed in Fourier transform. So, but I just say okay, say this is good, and so we have that. And so where you have omega t, this is called the Fourier transform of u. Okay, because we regard u as a function of x and t is parameter. So the Fourier transform will transform x to W function, right? Or omega function is fine. And so this is 1 over square root of pi uxt minus I omega x dx. Okay, so this is the Fourier transform. Okay. Right now we deal with this one, and we have so the Fourier transform of ut is equal to 1 over square root of pi ut So it's xt, okay, minus omega x dx. Okay, so this is 1. The partial derivative. Now, suppose we are able to exchange the integration and the partial derivative, the order of the integration and the differentiation. So we have okay, so we have that. Okay, so we assume that the order of the integration and the partial derivative is changeable. Okay, it's changeable. All right. So so what is this? Actually, this is U hat omega t. Okay, this you have omega t. Then we obtain an first order ODE. Okay, so that is U hat equal to minus c square omega square and the U hat. Okay, so this is U hat. Okay, now this is our. Okay, over here we deal with this one. This part has been dealing with. So the left-hand side is equal to the partial derivative of the U hat. Remember, U hat is what? U hat is the Fourier transform of U with respect to the x variable. So we have that. So this is a partial derivative. And the right-hand side is minus c square, omega square, and U hat. This is U hat. All right. So at this moment, we by regarding this term as a parameter. The frequency, omega, is a parameter now. Okay? So it's parameter. So this is immediately we can solve that. Okay? So that so this is implies that the solution is exponential function. So you have omega t is equal to constant c square t. Okay, and this is c omega. Because omega is a constant, so the integration constant, is a function of omega in general. Okay. So the solution of this ODE, because omega is a parameter, so it's fixed. So in this ODE, omega is just a constant, a fixed parameter, and so you have exponential function here as a function of t, like this one. Okay? Any question up to here? So I just do the Fourier transform. Okay? And then manipulate each side, and then we end up with first order ODE, very simple ODE. And when we solve the ODE, first order ODE, we get this one. Okay. So now, since C omega. What is C omega? Is U paid and omega is 0, right? So when t is 0, you get so C omega is U head omega 0. Okay. And so that is the Fourier transform of x, and the U x is 0. Okay, U x is 0 because the time parameter is 0. And what is that? By our initial condition, it's f of x, right? So this is what? This is just the Fourier transform of x. So C omega is just f hat omega. Okay? By the initial condition. Okay, so now we have U hat omega t is equal to f hat omega e minus c square omega square t for all omega in R and t greater than 0. So basically, we are almost to our destination because we have the Fourier transform of U x t with respect to x. So what we have to do is by taking the inverse Fourier transform. So taking inverse Fourier transform, okay, with respect to x. Right? So we have here U x t inverse Fourier transform of x. Okay. Okay. Now, by convolution theory, right? Because you have two omega function, so it may regard it. This is the Fourier transform of some function. This is another Fourier transform of another function with parameter t. So t is a parameter. Remember that? T is fixed as a parameter. So by the convolution theorem, so this is equal to 1 over square root of 2 pi. Remember the convolution theorem? The inverse Fourier transform of f a. Okay, convolution with okay. So basically, the inverse version of this product is actually equal to the convolution of two x functions. Okay, and we know what is that. So we have to know the Fourier transform. So you consider the Fourier transform here, Fourier transform of E minus A square, okay, is equal to 1 over square root of 2A E minus omega square and 4A. Okay, so that is the. So you can check the table of Fourier transform in chapter 11 to see there this one. Okay, so this is the Fourier transform. Okay, and so look at here. This is pretty much like this one. Okay, so when you compare, so what you need to know is that you want this is equal to minus omega square for A, right? You want this is for A. So this is implies what is A, right? So A is equal to Okay, so is that A is this one? Okay, and so A is that. So by relating A equal to 1 over 4c squared t, okay, we have Fourier transform of x e minus x squared 4c squared x 4c squared t. This one is equal to c square root of 2t and e minus c square over square t. Okay, so that we know that f Fourier inverse transform of e minus c square omega square t, which is equal to 1 over c 2t and times e minus square 4c square t. Okay, so we have that. And then the convolution. So finally, so u of xt is equal to 1 over square root of 2 pi f of x convolution with 1 over c square root t e minus x square 4c square t. Okay, so the convolution. And so this is equal to f of v and 1 over 2c, okay, 2 and the square root of pi t. With the product, we get 2 out of the square root and the pi t here, and the exponential x minus v, okay, square, and the 4 c square t. Okay, and this is equal to what we had before. So which agree with 12.7.6. So they agree. Okay, or you can take, so what need is 2 c square root t percent. Okay, let's stop here. And so the rest of this section is that we will solve the heat equation if the bar extended only to the positive infinite direction. So the x is from 0 to infinity. Okay. So next, the heat equation with x greater than 0, b greater than 0, with initial condition at x equal to 0, a boundary condition with a boundary condition ux u 0 t equal to 0 for all t, and initial condition u x 0 equal to f of x zero, such that f of 0 is equal to 0. So that means that the end, x is equal to 0, a boundary condition at okay, x equals 0. So at x equals 0, the temperature always is 0. So I said it is homogeneous, right? 0. But we still have an initial condition. Okay? But here, because of the boundary condition, the f0 should be equal to 0. Okay? So we will solve this equation, right? And the x is not from minus infinity, just x greater than or equal to 0. Alright, so we will use what? We will use Fourier cosine transform over Fourier sine. But because f0 is equal to 0, so it's better to use the Fourier sine transform. Okay. Of course, I think Fourier cosine is just fine. It's fine, but it's quite natural if we use the Fourier sine transform much bit later. Okay, this is because it's 0 in particular. It's 0. Okay. All right. So I think I will continue just a little bit rest of the section. Finish the section on Thursday. Any questions? Okay. No. Okay. So see you on Thursday.